Good evening and welcome to our third online webinar organized by the Young Chemists of the Royal Chemical Society of Belgium. Today we have the pleasure to welcome Dr. Alae Eddine Lakraychi, who is going to talk about positioning organic electrode materials in the battery landscape. But first of all, we would like to take the opportunity to present a bit ourselves and what our association is doing. So we are an association of young chemists of the Royal Chemical Society, mainly in the Federation Wallonia, Brussels. And our goal is to help young chemists, such as master students, PhD students, and postdocs, during their first steps in a scientific career. How? Well, mainly by organizing a variety of different events throughout the years, such as conferences, where we give you the opportunity to present your research and to exchange with peers, by organizing lectures, scientific lectures such as today, or lectures where we inform more about the best way to valorize your results and your personal skills, by informing about job opportunities. Usually we organize company visits so that you can get familiarized with the local chemical industry, and we also inform about job offers on our social media accounts. Our goal is really to create a link between academia and the local chemical industry so that it is easy to find collaborations or also a job after your studies. We also provide networking opportunities, and we really hope so to be able to organize a badminton tournament next year. In the meantime, we thought about some other kinds of events that we could organize. That's why we organized for the first time our video clip competition, which took place last month. And we are very happy to congratulate Perrine Weber from UMans, who won for her meeting with Pepto. So congratulations, you won 200 euros. If you are interested in what we are doing and you want some more information, you can either write us an email or contact us on social media such as Facebook or LinkedIn. Now let's talk about the webinar of the day, which is going to be about positioning organic electrode materials in the battery landscape, a credible alternative towards eco-friendly batteries. We are very pleased to welcome Dr. Alae Eddine Lakraychi, and I'm going to start by presenting our speaker. He did his PhD in material science at the University de Picardie Jules Verne in France, where he worked on the transformation and valorization of natural resources. Then he started a postdoc at the UCL under supervision of UCLouvain, where he started working on the conception of lithium-ion batteries. And now recently he started his second postdoc, still in material science, in battery science at the University of Houston. Today in his presentation, we are going to learn about the history and the working principles of organic electrode materials. We are going to speak about the molecular and device parameters governing the implementation of OEMs. He is going to speak about the possible battery assemblies suitable for these kinds of OEMs, the pros and cons of each assembly, and last but not least, about the advances and challenges. So thank you very much for accepting our invitation. We are very pleased to have you with us. To our public, please feel free to ask your questions in the Q&A section, and at the end of this presentation, we are going to answer as many as possible. So thanks a lot, and the floor is yours, Alae Eddine.
Thank you very much for this kind introduction. I just want to make sure if you are hearing me well and you are seeing my screen first.
Perfect.
Perfect. So as I said, thank you very much for this kind introduction. It is a pleasure for me to participate in this series of webinar. And today's talk message is to try to position the organic electrode materials in the battery landscape. So we researchers working in this field, we believe that organic batteries could be a credible alternative towards eco-friendly batteries. We will see at the end of this talk if you are convinced or not. But in any way, I hope that this presentation will be useful for you, and I hope that it will clarify the picture for those who would like to start in this field. So I'd like to start where the battery start back in the year of 1800, where when Alessandro Volta invented the first battery. So is the battery called Volta, which is based on a stacking of copper and zinc sheets with an electrolyte in between, and that was the first battery. Actually, this was the trigger for the battery research and development, because after this one, you had many battery technologies that had an impact and still having an impact on our lifestyle. So the first one was invented in the 1859, which is the lead acid, and we still use this battery technology in our gasoline car to start the engine. Then you have the nickel cadmium and the nickel metal hydride, mostly for the power density applications. And then you have the most popular one, which is the lithium ion. And here I would say is the revolution. And thanks to this revolution, it won the Nobel Prize in Chemistry in 2019. And this Nobel Prize was awarded to these three gentlemen, Prof. John Goodenough for the lithium-containing cathode, lithium cobalt oxide, and then the Prof. Stanley Whittingham for the concept of intercalation chemistry, which is the foundation of the lithium-ion battery, and then for the Professor Akira Yoshino for the battery assembling and prototyping of the first lithium-ion battery at Sony in 1991. So as you can see, in 1859, the energy density of the battery was like 25, 40 watt-hour kilogram. And then we start growing till 1991 with an energy density value close to 100 and 150. So you can see that the single parameter governing the development and evolution of the battery technology was the energy density. So, well, it's still the energy density, but now we do have other two parameters that we need to take into consideration for the battery research. So here I'm talking about the cost. So if you want to make an impact on the electrification of our lifestyle, so we need to make it affordable for all the population. So cost, because here we will produce billions of units, so the cost should be lower. And the second important parameter is the environmental footprint. For the current lithium-ion battery that we buy, it still uses some scarce materials or scarce elements with higher energy fabrication process. So it consumes a lot of energy. So here, the three parameters so far are the energy density. We are looking for higher energy density, low cost, and low environmental footprint. And this actually calls for other battery technologies beyond what we call the post-lithium ion or beyond the lithium ion. So first, we want to improve the energy density of the lithium ion. So far we are looking for 150, 300, even more. And by doing this, we will try to remove cobalt from the cathode material. Some interesting research are going on NMC, nickel manganese cobalt oxide. So the cobalt percentage should be as low as possible. And by substituting or replacing the graphite that we use actually in the anode by silicon, and silicon will provide a high capacity. So by combining these both electrode materials, you can end up with a large energy density. And if you have a large energy density, you will still provide the same energy by using fewer materials, and here you will reduce the cost across the board. Then, lithium is scarce. It's not that much abundant. You can still keep the same configuration, which is metal ion, and you shift to another more abundant elements. So we can talk about sodium ion, for example. And here there is already a commercialized sodium ion battery in France with a company called Tiamat Energy, and they can provide sodium ion batteries with 75, 150 watt-hour per gram with a good power density as well. Then you have the lithium sulfur and lithium air batteries. So those ones are very promising because they provide energy densities at least 6 times, 10 times of the current energy density of the lithium ion battery. And sulfur is more abundant, so it would be cheap, and air is the same. So the environmental impact and the cost will be reduced for these very technologies. And then we have the organic material. So, organic materials could be based on renewable resources, could be generated from biomass. And in addition to that, some organic molecules can provide moderate to high energy density. So this is actually a good alternative to take into account for if you want to make a battery with the high energy density, low cost, and low impact of energy, of environmental impact. So maybe some of you might think that's because I'm presenting this as future batteries. So maybe some of you will think that this is a new battery technologies that are showing up in these days, but actually it's not, because if you take the organic material is as old as the lithium ion battery. So the first report on organic electrode materials was published by Williams in 1969 by using this isocyanuric acid versus lithium metal. And the potential at that time was 3 volt for this molecule. And he showed that we can use organic materials as electrode materials to store energy. So shortly after, there is the electroactive polymers or the conductor polymers. And here, one of those polymers, which is the polyaniline, was actually commercialized and they removed from the market. And after this, here, I would call that the dark period of organic materials. So there is no report on organic materials after 1977. And the reason behind that is that it's because the success of the inorganic electrode materials. Remember, 1991, we have the first lithium-ion battery. So the whole world was excited. We have a lithium-ion battery. We can do this. We can improve that. And then others, they will try to understand more this battery technology to improve the energy density, to find new electrode materials that can substitute lithium cobalt oxide, maybe graphite, to try to understand other phenomena. So all the battery scientists were like busy and more focused on inorganic electrode materials. And this happened until the year of 2008, because as I said, we introduced a new important parameters, which are the cost and the environmental impact of the battery. And this 2008, it witnessed a revived interest in organic batteries, which was triggered by Philippe Oiseau and Jean-Marie Tarascon, Michel Armand, with the seminar paper published in ChemSysChem. They show that they can use an organic materials derived from a biomass source, and you can use it to store energy with the high energy density, and then you can recycle it. And as you can see with this nice picture below. So beyond this year 2008, so organic batteries are witnessing a speedy development. Here today, we are talking about more than 50 review articles on the topic. So you can imagine how many articles published so far in organic batteries. So contrary to the inorganic or the lithium-ion batteries, as I said, we will replace the electrode by scarce inorganic materials with light element organic materials. You can move from manganese, cobalt, nickel to carbon, nitrogen, and sulfur. So those are more abundant, are light, are cheap. So other thing is that thanks to the flexibility of organic materials, you can move from lithium to sodium, potassium, magnesium, and calcium. So we can use other charge carriers. So the advantage of the organic batteries, thanks to the organic chemistry and the flexibility of the molecules, you can tune the redox potential. You can make them as a cathode, as anode. We are going to see this in a moment. And then you can store, by adding multi-redox functions, you can store multi-electrons, and this leads to high capacity. And you can use them as a bulk or a polymeric materials. And this actually will give you access to a more design, which you cannot do with the inorganic materials. Here we are talking about flexible batteries that would be more important for applications in the Internet of Things, for example. Of course, it has some inconvenience, and most of the organic molecules are soluble in the conventional electrolytes. You know, electrolytes are organic solvents based on organic solvents and metal salts. So most of the organic molecules are soluble in those electrolytes. Then most of them are insulator, so they have a low electronic conductivity, but the most or the major issue is the volumetric density. It's very, very low. So I think that we are not going to see organic materials in the electric vehicle because the size of the battery would be large because of the volumetric density, but they are light and they can provide a higher energy density for other applications. So contrary to the inorganic materials, for the inorganic materials, you can store energy by intercalating ions in the crystal structure of those inorganic materials. For organic materials, you store energy by charge compensation. And based on this charge compensation, we can classify redox mechanisms according to a unique classification. So the first one is called N-type. And here the redox reaction is evolving between a neutral state of the molecule and a negatively charged state of the molecule. And here, since you have a negative charge, you need a cation for a charge compensation, and you can exchange the cations back and forth during the redox reaction. And this cation would be proton, lithium, sodium, potassium, magnesium, for example, which means that with the same molecule, you have access to different battery technologies, and this is the power of the organic materials. And here I'm showing you an example below for the Kano here, and then you have the second one we call the P-type, and here the redox reaction is evolving between neutral state and the positively charged state. So here you will not exchange cations, but will exchange anions that are present in the electrolyte. And I'm showing you an example below called conjugated amines. And then you have other molecules or redox functions that can work at both P-type and N-type. I mean, with the same redox function, you can either store an ion or store cations. And those kind of molecules are belonging to a bipolar type mechanism. And the most famous example is the radical nitroxide. So based on these three different redox mechanisms, actually we can have multiple redox classes. So here I'm just showing you different organic material, different classes of organic electrode materials. And keep in mind, within each class, you have dozens of molecules. So the database of the organic batteries can be extended to hundreds of molecules. So the choice is versatile, is large. As you can see, you have some molecules that have a high potential, redox potential, 4.0 volt versus lithium, for example, others with high capacity, and we do have others at low potential with high capacity as well. So since we have this big library of organic molecules, so I think that we can combine a cathode from here and an anode from here with an electrolyte, and we make a full or all organic lithium organic batteries. But the question is, which configuration can we use to implement those organic molecules? Well, so here there are four possible organic battery configurations. If you want to use organic materials as the main electrode material, there are four possibles. So the first one is the metal organic battery, then the dual ion battery, the anionic rocking chain battery, and the cationic rocking chain battery. So each battery configuration has its pros and cons, challenges and advantages. So I'm going to show you an example on the metal organic battery and the dual ion battery, another one on the anionic rocking chain battery, and I will talk a little bit more about the cationic rocking chain battery because most of my work was in this direction, and this one is more close to the current lithium ion battery and is more practical. Okay, but before that, I just would like, for those who are not familiar with the battery research, I just would like to remind or to introduce some parameters that we are looking for in the battery research. So we have the targets on the right and we have regulations on the left. So for the targets, we are looking for high energy density. And this energy density, we can calculate it based on the product of the voltage and the capacity. And this is, we give the autonomy of the battery. Then we look for the power density, which is how much energy can the battery deliver in a shorter time. For example, if you want to charge the battery, you want it to have it done in few minutes, or you have to wait for hours. And then you have the safety. The battery should not explode, should not have some safety concerns. Then there is the battery life. So you just want to buy a battery that will last for months or even years. You don't know, you don't want to change it every 2 weeks or 5 days. And then you have the cost, should be at affordable cost. So in order to have these targets, we have the regulations. So we should look for our materials. This is in general, not only organic materials, but in general. We should look for electrode materials that can provide high capacity. And how is that? We look for organic or general electrode materials that have a low molecular weight and can exchange as much as possible of electrons. Because here we have the formulae on the left, based on the number of electron exchanged and the molecular weight, we can calculate the capacity, which can be expressed by ampere hour per kilogram. Then you have the voltage, which is the difference in potential between the potential of the cathode and the anode. So the potential of the cathode should be as high as possible, and the potential of the anode should be as low as possible. And by doing this, you can maximize the voltage, and then this voltage capacity will give a direct access to the energy density. Then you have the kinetics, and this depends on many parameters to the electrode, to the many parameters like for example the solid, the ion diffusivity in the solid, the kinetics of the redox reaction itself, and this gives direct access to the power density. And then we have the stability, which is the structural stability and the electrochemical stability of the material during charge discharge cycles, and this gives access to the battery life, for example. So after that, I'm going to present the metal organic battery. So here we have the positive electrode is based on organic materials, and the negative electrode is based on a metal, which is solid. And both of them can store cations. So during the charge, what will happen, we remove cations from the organic electrode and you put them on the solid metal anode electrode. And during the discharge, you will remove the cations from the anode electrode and you put them on the organic positive electrode. So the example here, the most famous example is the lithium metal. Why? Because the lithium is the lightest element, so it gives a high capacity. Here we are talking about 3,600 milliampere hour per gram, and it provides the lowest potential. On the other hand, we have organic materials that can provide high capacity up to 500 milliampere hour per gram. So if you combine an organic cathode material with a lithium metal anode, here you are talking about high energy density. So it's very, very, very promising, but it's very, very, very challenging. Why? Because based on the electrolyte that you use, when you use lithium metal as anode, you start growing what we call lithium dendrites. And this is the kind of things that you see growing on the surface of the anode on the left. And then it goes through the separator and it touches the organic electrode. And if you have that, then you generate an internal short circuit, and this causes the battery to heat up and then to explode. For the cathode, those cathodes that can provide 400, 500 are mostly soluble in organic solvents. So after the second, third cycle, you will have no more cathode, and then the battery will be dead. So the main challenge I would say here is the electrolyte. We just need to find an electrolyte that can support or can overcome these issues. But lithium is good. You have more than 3,000 milliampere hour capacity, low potential, but the abundance of lithium is very low, and you can't find it in very large places. I mean, it's available in only very few places, and this, if we rely all the very research on lithium, so then we will have some geopolitical problems in the future, and the cost will be higher. Fortunately, there are other alternatives. We are talking about sodium, potassium, or other multivalence, because with the lithium you have only one charge. With the calcium, magnesium, or aluminum, you have two charges or three charges. So during the same redox reaction, instead of one electron, you can store two or three electrons. And this will give you access to high energy density. And another factor which is very important is the volumetric capacity, which is very important for the electric vehicle. And the aluminum here is providing the high volumetric capacity. So what you need to do here is just to compromise. You just need to look what are you looking for, which application, and you just compromise. You need low cost, energy density, and then you choose which metal you would like to work with. Another parameter to take into account with these metal batteries is the deposition morphologies of the metal. You know, when you use the metal, it's like a solid substrate. It's not a host structure. You will not have the ions coming in and out. So what you will do is that you will deposit and strip the metal cation at the surface. So what we are looking for is this homogeneous deposition and stripping, which is very good, and this will continue the battery to work, and we'll have a good yes, working. Then, independent on the electrolyte chemistry and recycling conditions, we have this metal dendrites that I talked about before, and then we have this random flakes or spherical or wires that you can deposit. So we want to avoid this because this will cause short circuit and will cause the loss of energy density during cycling. So based on this best homogeneous, I would say, deposition stripping, I will show you an example with magnesium, because there is some interesting work on magnesium with that. But before, please keep in mind that magnesium holds twice the amount of charge than the lithium plus or lithium ion, while having a similar ionic radius. What does it mean? It means that you will have a hard ion dissociation. It's very hard to find some magnesium salts that can dissolve in organic solvents. And then you will have a slow solid state diffusion. And sometimes instead of storing magnesium ion alone, you will store magnesium salts with the chloride, magnesium chloride or something like that. And this will lower the energy density. So those are the challenges, the main challenges for the magnesium metal battery. So here, thanks to the work of my current supervisor, Dr. UCLouvain, I'm going to show you an example paper that is tackling these three issues. So he's using the magnesium metal and the weakly coordinating electrolyte with the high energy density organic material as a cathode material. So for the positive electrode, you start with this, what we call PTO, organic electrode with the carbon at the electrode. Then this one is slightly soluble. So once you reduce this, and you see in the middle, you will reduce this 2 carbonyl here, and then you catch a magnesium ion. Once you do this, this complex will dissolve. So here you have a liquid phase. And this is a very crucial parameter for this redox reaction. We call it the heterogeneous ionization redox reaction. And after that, once you reduce the 2-second carbonyls, you will accept another magnesium, and then you precipitate the compound. So you start with slightly soluble phase, completely soluble phase, and completely insoluble phase. And this actually provides a high energy density, as you can see above, high capacity, as you can see above with this galvanostatic curve. Second one, you need an electrolyte that is low viscous and can do the job. I mean, can protect the surface of the metal magnesium from growing dendrites and all of this. And for this, you need to do a screening of the electrolytes. You just need to mix, to find an electrolyte formulation that would dissolve this magnesium salt and have a low viscous and high ionic conductivity. So thanks to this hard work, so they found an electrolyte formulation based on what we call MMC as a magnesium salt that you dissolve in a mixture of solvent, DME, dimethyl and diglyne. So if you use this electrolyte, you can have what we call a good deposition and stripping of magnesium. And here you can have a high stability of this. And then, as you can see on the right image below, you have no magnesium dendrites growing. So you have an homogeneous deposition and stripping, and you can always do this at high current density. And this is very, very important because you are going to see in the next slide why is that is more important. So based on this combination of this organic cathode, electrolyte, and magnesium, you can make a magnesium battery that delivers a specific power of 30 kilowatt per kilogram. And this is a record for magnesium batteries. If you talk about organic or inorganic, is the highest power density with that is published so far in the literature with magnesium batteries. And as you can see, this is the full cell. It's completely reversible. You have 300 million per hour per gram, and on the right you have a better stability, more than 200 cycles, so which is a good battery. So if we compare this with other magnesium batteries, so you have on the left magnesium batteries that are based on sulfide. So most of them, they require high temperature for cycling. Then you have sulfur on the top in blue, that provides more energy density and power density. And then you have the organic magnesium batteries that can provide much more energy density and power density. And here this is what we can do with organic materials. Then we have the dual ion battery. So here you have the organic, the cathode or the positive electrode that is based on an ion storage cathode. So here, instead of storing lithium, for example, you will store the anion that PEP6 minus or perchlorate. And on the other side, you will have an anode material that can store ions. So here during the charge, for example, the cathode will uptake an anion and the anode will uptake a cation. And during the discharge, the anode will release the cation and the cathode will release the anion. So the working principle is different from the previous one. And for this, you need a large amount of the electrolyte, because by doing this, you will change the concentration of the salt in the solvent. And if you do this, you will change the ionic conductivity, and then the battery performance will be worse. So that's why it requires a large amount of electrolyte. So what is the important thing with this dual ion battery is the high voltage. Why? Because we can reach voltages between 2 and 3.5, thanks to the high potential of the cathode material based on a P-type material that can store anions. So here all the potentials are higher than 3 volt. And we can use anode materials that have lower potential. And here you can maximize, you remember the voltage is the difference between the cathode potential and the anode potential. So, but the challenge is this cathode materials store bulky anions, so you need to consider the molecular weight of this anion, and then the capacity will drop. And most of them, they don't provide a much higher capacity. And the second thing is that you just need to use a large amount of the electrolyte, and this will add additional cost to this very system. So this is the advantages and the inconvenience of this battery configuration. I'm going to show you an example based on what we call a bipolar electrode material. So this bipolar, remember, this is a molecule that can use two different redox functions. One that can store anions and the other can store cations. So the one that can store anions, we can use it for the positive, and the other one for the negative. And if you use these bipolar electrode materials, it will be helpful for the fabrication process. So the fabrication process will be simplified, and this will reduce the manufacturing cost, because you just need to put the same electrode, exactly the same electrode in both electrodes, positive and negative, because both of them, they can act as positive and negative, and you can reverse the polarity of the battery. So it's very, very important. So this one, the starting molecule is in the middle in black. If you go right, you go for high potential. So you use it as a cathode or a positive electrode. And here you store anions. If you move to the right, you will use it as an anode thanks to the carboxylate, and you will store lithium, and this will happen at low potential. So the figure below is the galvanostatic charge discharge of this molecule when used as a positive electrode and negative electrode. So the red one is corresponding to the scheme on the right. So you have a high potential above 3 volt with a specific capacity of 100 milliampere hour per gram. And the second one, or the one below in blue, is corresponding to the carboxylate, the one on the left on the scheme above, and is corresponding to the negative electrode. And on the right, as you can see, you have a good cycling stability of this both. I mean, with the same molecule when is used as a cathode or anode. So if you combine this to make a full organic symmetrical cell, so you have this kind of curve which shows the reversibility, because sometimes, you know, when you make a full cell, you need to have a cell balancing, you need to have the same amount of energy at the cathode level and the anode level, which means if you are using two different materials, maybe you will require to use much more mass of the material in the cathode side and lower mass in the anode side. But for this symmetrical battery, you will use exactly the same mass, because you are using the same molecule and you are providing the same energy density. And as you can see, this on the right, the cycling stability goes to 200 cycle. So this is a very, very good example to show for this dual ion battery. So this symmetrical dual ion cell delivers a voltage of 2.5. As I said, it is a good voltage for organic batteries, but the challenge is the specific capacity is still a little bit low, 53 milliampere hour per gram. So the research here is trying to increase this capacity and a little bit increase the voltage, and by combining this, you will end up with a high energy density. The third example is what we call the anionic Roentgen battery, or what is known as a molecular ion battery. And here, actually, we are talking about the true all-organic battery, because the previous examples that I have shown you, we are still using metal cation in the electrolyte. So it's organic, electrode are based on organic, but we have a little bit of the metal. And here, so we can avoid this because the battery will store only anions. So that cation that we are using is metal-based, so we can use an organic-based cations. And here we are talking about all organic battery. So this concept was first introduced by Masaru Yao, is a Japanese group in 2015. And I'm going to show you another example. So one of our collaborative called Philippe Oiseau is working on this, and I'm going to show you what kind of work he has done on this direction. So, but before that, you know, many challenges on this battery configuration, because, you know, it was just introduced in 2015. You know how many people working on this, but the advantage, I would say, of this is that you can use a metal-free electrolyte. Electrolyte would be cheap, and you can take advantage of the high potential of the cathode because they are p-type based and they react at high potential. But the challenge is the negative electrode. Why? Because for the moment we have only one negative electrode that is suitable for this battery configuration, and it reacts at higher, relatively higher potential, higher than 2 volt. So the voltage, or the output voltage of this battery configuration will be low. Here we are talking about 0.51 volts, so it's very low. But it's a good direction for if you want to really make a green battery with a metal free. So the example that I talked about is this one. We are using a Voyologen derivatives and with a conjugated amine as a positive electron. So for the conjugated amine, here we introduce as you can see in red, a carboxylate, which is the ionic group. We use this to prevent the solubility because here we have a small molecule, and if you don't use this ionic group, it will dissolve. So if you want to prevent the solubility in the electrolyte, you add these ionic groups. And by doing this, you will have a stable molecule in the electrolyte, and you can charge it. For one electron, you reach a capacity of 75 milliampere hour per gram. And then if you add a second electron, then you will reach a capacity 150 milliampere hour per gram, which is not bad actually with the potential of this molecule. So in practice, this on the left is the galvanostatic charge discharge of this molecule. So it reacts at an average potential of 3.22 volt, which is pretty much good. But the capacity is a little bit lower. It's 75 milliampere hour. So this one is limited to one electron. I mean, practically, if you want to reach the second electron, you need to go higher in voltage, and you do this, you will form another molecule which is highly soluble in the electrolyte, and then you will lose the stability. So in order to have a good stability, you will limit in one electron, and then you will provide only 75 milliampere hour per gram, but is stable, as you can see on the right graph here. Another advantage of this molecule is that you can use it without addition of any carbon. You know, as I said before, organic materials are insulators. So in order to have electronic conductivity, you add carbon, conductive carbons, and sometimes we add a large amount of these carbons. We are talking about 30%, 40%. And this actually decreases what we call the mass loading. But with this molecule, you can use almost 100% of the material is the carbon-free and the binder-free. And this will increase the mass loading of this electrode. And as you can see, this is a test with the carbon-free electrode, which still provide almost 70 milliampere hour per gram with a good stability over 100 cycles. For the negative electrode, as I said, Viologen are the only available negative electrode chemistry for this Berry configuration, and this is how it works. So you start with the molecule that is positively charged. You have an anion for charge compensation. So you start with a discharge. You remove the anion, then another discharge to remove the second anion, and you end up with this neutral molecule. But if you use it as such, actually, this one will be soluble in the electrolyte, and then you will lose in the cycling stability. So if you want to make it stable, it's the same thing. We will add an ionic group, which are the carboxylate. And this work has been published in On to Chemistry, and is a nice work because it shows the real how can I say the real possibility of this Viologen to be used as anode material for this molecular ion Berry configuration. So here is the same redox reaction. So in practice, as you can see on the left, you have the potential versus specific capacity curves. So you start with a discharge at 2.5, you remove 1 perchlorate. Then you start with a second discharge, you remove a second perchlorate. And you can do this reversibly. So take out, take in perchlorate. But how can we show that we are really taking electrolytes and not something else? And here we do a kind of experiment we call ex situ FTIR. So we monitor the redox reaction by spectroscopic techniques. So here we will start at at 3 volt. So is the spectrum above on the top. So you can see here that you have the carboxylate remain unchanged during the redox process. So the carboxylates here are not participating in the redox reaction, but instead you can see the bond around 600, which belonging to the perchlorate anions, appearing and disappearing. And this actually proves that you are taking in and out perchlorate anions, and this proves the anionic redox mechanism. And then if you combine this conjugated amine with the viologen in a full organic molecular ion, you will have this kind of curve with the voltage around 0.7 volt. You have a good reversibility, and you have a good, or I would say excellent cycling stability over 100 cycles. So this molecular ion, which still delivers a low voltage, 0.7, as well as a low specific capacity of 27 milliampere hour per gram. And here the energy density is very low, 24. But the concept is good. Too many challenges are here, but we just need to find some suitable anode materials that can react at low potential, and here we can increase a little bit the voltage, and we look for high capacity materials. And if we do this, we will be able to provide a true or organic batteries cheaper with high energy density. But the challenge is very big, but we still have time to find to try to overcome these challenges. Then we have the most promising one, which is the cationic Rocking-Share battery. We call it the metal ion, lithium ion, sodium ion. And here is exactly the same as the lithium ion. In the positive electrode, you need a lithium or a metal containing electrode. So it needs to be made at the discharge state. So here you will remove the lithium from the cathode, and then you take it to the anode. And during the discharge, you remove the lithium or the metal ion from the anode back to the cathode, and you can do this. So this battery configuration can provide moderate voltage, I would say from 1 to 2.5. This is what we can do currently, but we are hoping for the better, increase it to 3 volt if we can. And at the anode level, we have a large choice of the materials that can react at low potential. I'm going to show you some examples of this. And then at the cathode side, we have some cathode materials that can be used for this configuration, and they can provide moderate to high potential. And here you can use a conventional electrolyte. You don't need to work on the electrolyte, but the challenge here remains at the cathode, because we need to find some metal containing cathode materials that are high voltage and air stable. So for the anode material here below, I'm showing you the different classes of organic anode organic electrode materials. The most promising one is the carboxylate here below, because it provides a low potential and high capacity. And if you take the general molecular structure of this, you have the carboxylate that you cannot change. Then you have the spectator metal cation, you have the aromatic, and you have the substitution that you can put in the aromatic. So these 3 parameters, you can play with them, you can change. And if you change the metal cation, you will have access to the cycling stability. You can have carboxylates that will cycle pretty much better than the others. If you change the aromatic system, if you move, for example, from benzene ring to naphthalene or pyrrolene, you will have access to the rate capability, which is directly linked to the power density. And then if you put the substituents on the aromatic system, here you will tune the potential. If you want to reduce more the redox potential, you just need to introduce electron rich substituting groups. And these are some examples based on this research on molecular design strategy. And if you would like to have more information about this organic negative electrode, I have a review that will be published very soon, and is dedicated to only organic negative electrode materials. Now, go back to our organic lithium ion positive electrode. So here we have what we call the gionological tree. So I'm going to show you, based on organic chemistry and molecular design, we will have many molecules that will be suitable for this application. I mean, to be used as a lithium ion organic positive electrode. So the first efficient reported lithium ion organic, it dates back to 2013. It was published by Poiseux's group, and it's a very efficient molecule Below you have the cycling curve of this molecule, so it's perfect reversible, and it has a low polarization, and potential is 2.55. And another important thing with this molecule is the synthesis, because here you can obtain this molecule from a biomass source, which is glucose, and thanks to eco-friendly synthetic procedure, you can produce this molecule by just involving carbon dioxide sequestration, and then this process is completely recyclable. But the problem with this molecule is the processability. If you want to process this material, you need to do it under air. But what happened to the molecule when you expose it to air? It gets oxidized, actually. Here I'm showing you the air reactivity that we monitor with IR spectroscopy, and you can see after 3 hours of exposure in air, you have the formation of a carbonyl bond, and this characterizing the oxidation of this molecule. So here we just need to have the same molecule, but it should be stable. How can we do that? So here we have a 2.91 volt, which is the oxidation potential of oxygen versus lithium, because you have a lithium containing, and this lithium will react with oxygen, and then this happens at 2.91. If you want to avoid this, your organic molecule, lithium containing organic cathode molecule, should have a higher potential than this value. If everything below this value will be air oxidation, and this will cause some problem for storage and processing, because you need a glove box to do this, and this will increase the cost of fabrication. So what we are looking for is lithiated cathode organic materials that can react at high potential, mostly above 3 volt. So there are several ways. We keep working with the same molecule. We have a lithium enolate carboxylate. So what we need here to do is just to try to change the molecular structure and try to find ways to increase that potential. So the first way is just to change the isomery of this molecule. Here you have a para configuration. If you shift from para to ortho configuration, you will have an increase of the potential of 3 millivolt. So here you have a 2.85 volt, but it still is not enough, because this one is lower than 2.91, and this one is not stable in air. Then you can replace the carboxylate here with another electron withering group. Here we have tried the sulfonate, and as you can see, we can produce a high potential. Here you have the line of 3 volt, and this one is the reacting above this one. And that's why this molecule is stable, not in air, in oxygen, because it doesn't react with oxygen, but it is unstable to moisture. It takes some water from humidity, and then you will have a worse performance. You still, process this molecule, need to process this molecule in a dry room. And after that, you keep the same molecule here, which is I would say the reference, and you substitute the spectator metal cation. Here, instead of putting lithium, you put magnesium, for example. And by doing this, you will change the electron density of the carboxylate. It will become very low, and this will increase the potential. And here we have a huge increase of the potential, almost 800 millivolt, and you have a material that can react at a potential of 3.4 volt, which is air stable, moisture stable. So it's very, very good. But the problem with this molecule, it shows only half of its capacity. So it should have 250 or more than 200 milliampere hour per gram. Here is showing only 100 milliampere hour per gram, so 120 milliampere hour per gram. So it's very, very low as compared to the theoretical value. And then you have another one based on diacetylene substitutes. And here, thanks to the electrostatic effects between these two oxygen that we have shown in the paper, they are very close. Then here you have an electrostatic interaction, and this actually causes an increase of the potential by 800 millivolt. So here the material, it still shows a large polarization, but here you still have the two electron reaction, so you can have a high capacity, but we still need to work more about the stability and improve the electrochemical behavior of this molecule. So all of these molecules are based on one class, which is the lithium enolate. As you can do at some points, you are stuck. You can't do too much, we change the substituents, we do electrostatic effect, we change the spectator cations. There is not a big room left to design this to improve the potential and improve the performance, electrochemistry performance of this lithium enolate class. So here we need to move to another new class. We need to design to find a new redox system that can be lithiated, can react at high potential, and can store energy or cations reversibly. And the way to do that, you just need to look on the molecules. So on the left is the one that I just shown you. And as you can see, this one is showing 2.7 volt. And those are belonging to what we call the Warsaw type redox system. It's based on an aromatic. And if you change what we call the ending group, here you have a carboxylate, so the potential will drop to 0.9. If you change it with the cyanide group, this will go to 3.3. So depending on the chemical nature of the ending group, the potential will be up or low. Remember, we are looking for something that can be, prior to do any molecular design, intrinsically should have a higher potential, above 3 volt and lithium containing. And if we look at this conjugated amine, it has a potential of 3.2, but it's not lithium containing. But as you can see, there is a proton here that can be substituted with lithium. And this actually will help us to design a new class of organic materials that is lithium containing, high voltage, and reversible redox reaction. So this one, if you use it as such, it will not store cations, it will store anions because it belongs to the p-type redox mechanism. It's not lithium containing and it gets oxidized in air. But below, on the other hand, we have another electrolyte chemistry that is very, very well studied. It's called lithium TFSI. So this one is air stable, lithium containing, but the redox is not reversible. So those characteristics are complementary, I would say. So if you merge actually this with this, you end up with something like this. We call it conjugated sulfonamide. And this is a new class of electrode materials that we have published in Nature Material. And it can have a high potential, lithium containing, and air stable. And above is the first generation of this of molecules belonging to this class of material. So here I'm showing you the reference molecule. We call it lithium PDSA. So on the left, you have the one that we synthesize. Is a lithium containing, air stable. So you will remove one lithium, and then you will form this intermediate molecule, which is a radical anion species. And then if you remove the second lithium, you end up with this neutral, fully oxidized molecule. So we will be able to synthesize both the lithium containing and the fully oxidized. And if you take them and you test the electrochemistry on both molecules, let's say, for example, liquid CV. So as you can see here, you will produce exactly the same curve. And this actually proves the perfect reversible process of this molecule at the electrochemistry level, but as well as at the chemistry level, because we characterize this with NMR and IR spectroscopies. In terms of varied performances, so the reference molecule can react as a potential above 3 volt during the oxidation, but during the reduction, which is the discharge process, we have a kind of a voltage hysteresis. For the moment, we don't know why we have this. It's remain unsolved, but it's a good material and it shows a good stability above during 50 cycles. Then the other molecule, if you add additional sulfonamide groups, so here you will have a perfect redox reaction with a perfect electrochemical behavior. We have exactly 2 electrons, low polarization, potential is a little bit lower, 2.7, 2.8, and this because, you know, the sulfonamide, the additional sulfonamides will act as electron donation and will lower the potential. But thanks to this, you will have an additional good stability. You can compare this one below with the one above. The one above, you have a slightly of the capacity loss, but this one you have a straight line. And even better, with this molecule you can cycle at high rate. Here we are talking about 2 lithium in 1 hour, that you can exchange 2 lithiums in 1 hour, and you can do that during 1000 cycles. So this one is very, very promising. We do have other examples based on this molecule on sodium, magnesium, potassium. So it's you are going to see some nice work on this molecule in the literature very soon. And the second thing is that one of those molecules actually can be comparable to the state of the art, which is the lithium iron phosphate in terms of energy metrics. So the energy metrics are the voltage, capacity. So this one can provide the same capacity, pretty much the same voltage, but it suffers from the stability. We are working to try to have this stable during cycling, and then we will see how if we can make some electrodes with the same mass loading as compared to the LFP. But this remains a big advance on the lithium-containing cathode material. So here, there is a new redox function that we are working on in the lab at UCL. I'm sorry I cannot show you the molecule now because it's still unpublished work, but I will just show you the electrochemical performance of this molecule. So this molecule is lithium containing, is air stable, and exactly the same characteristics as the previous ones, but with a different chemistry, with a different, redox fraction. And this one actually can store high capacity. You are talking about more than 300 milliampere hour per gram if you exchange 2 electrons or 2 lithiums, and the potential is pretty much at 3 volt. But, capacity is more, we have a moderate stability after 50 cycles. So what you need to do here is just to work on the electrolyte and on the electrolyte formulation in order to make it stable during cycling. Here is another molecule that is belonging to the same redox class, and as you can see, we have good capacity. So the good news with this redox function is the high capacity with the lithium containing and sometimes the high voltage characteristics. So in order to compare this, so our target for lithium containing organic cathodes is LFP, lithium iron phosphate. We want to make something that can behave exactly as lithium iron phosphate, can provide the same energy density, the same power density, and we can process it as lithium iron phosphate. So now we do have pretty much, molecules. In 2015, we had only one that is very low as compared to lithium iron phosphate. Today in 2021, we do have many chemistries. Some of them are lower, some of them are comparable, but others, they can be even better than lithium iron phosphate. We just need to work hard on them in order to improve even more their electrochemical performances and processability. So here I come back to our genealogical tree. So before it was empty, now we do have different classes, different molecules, different chemistries, but keep in mind that thanks to the richness of organic chemistry and the molecular design, there is a big room left to design new redox function with this lithium containing. So we just need to focus our research, and actually our lab in UCL and France, they are working in this direction, and I'm pretty much sure that you are going to see some additional chemistries with new redox functions, and in order to enrich the library of the lithium ion or the lithium containing organic positive electrode. So to summarize, I have shown you that we can implement organic materials in 4 possible battery configurations. The first one is the dual ion battery. And this one, the most important thing that you just need to keep, if you want to work in this field, this one is the high voltage. But the challenge here is the electrolyte and the capacity. You need to find some p-type materials at the cathode material that can store high capacity. And the other one, you have the lithium ion battery, is more promising, can provide a moderate to high energy density, but the challenge here is the lithium containing cathode. You just need to have a lithium containing high voltage and air stable cathode. And the other one is the more, even more promising, is the metal battery. So here you can target high energy density, but the biggest challenge I would say is the electrolyte. So here, if you have knowledge on electrolytes, most of the research are going on solid electrolytes, and actually this would be my topic of research during this postdoc here in the University of Houston with Dr. Yao. And here we can provide a high energy density based on organic materials. And the other one, which is the molecular ion battery, is the true organic battery. You can have a low cost, eco-friendly battery, but here the challenge is the low energy density, low voltage, and if you have knowledge on organic chemistry and molecular design, you will try to design some negative electrode materials or molecules that will be suitable with low potential for this very configuration. Of course, I cannot finish this talk without acknowledging all the professors, postdocs, and students that I have worked with during my moderate career, because I just started. And with that, I'd like to acknowledge as well all the universities, the source of fundings, and the Association of Jean Chimists to give me this opportunity to to share with you this work and to clarify the picture for you about organic materials. And with that, I would say thank you very much for your attention.
So thank you, Aladdin, and congratulations for this very nice talk. So personally, I had some questions before your talk, but I guess you really did well, because many of them have already been answered during this, so it was really complete. And so I guess I should say good morning to you, because you are in Houston for the moment.
Yes, it's a morning for me.
It's the morning. About 11 o'clock, if I'm right.
Exactly, 11 o'clock. So I still have sun here.
You have sun in Houston, so you are a bit lucky, because here it's more snow in Belgium.
Yeah, this is what they told me. You have Christmas now in April.
Yeah, that's it. Strange, but
yes.
So hopefully the connection was really good, even if you were in Houston. But I'm a bit sad about it, because it would have been a nice opportunity to say the very nice sentence, Houston, we have a problem. But this is for next time. So now I propose that we go a bit deeper into the questions that have been asked. First, 3 questions that concern the solubility of the organic compounds at the electrode. We have a question from Deepak Gupta and also Abdel El Kabraichi, who ask how to deal with solubility issues of organic electrodes, and do you have any solutions for it?
Yes.
Tackle with the solubility concern.
Yes, of course. So there are several ways, all depending on your know-how, on your background. How do you want to tackle this issue? If you are organic chemist, I mean, you can try to design some organic materials that will not be soluble. And here we have 2 ways. You take the small molecule and you add ionic groups. I already shown an example during my presentation, and those ionic groups could be carboxylate, sulfonate, because you polarize the molecule, and by doing this you make it insoluble. And this has been proven with many molecules in the literature. And the second one is, you have a small molecule, you will try to make it a big molecule, and here we are talking about polymers. So here you can make a large molecular weight materials, and by increasing the molecular weight of these materials, you will decrease the solubility. And the most of there are plenty of examples of molecules of research work doing this. I mean, you just need to polymerize, but the inconvenience with the polymerization is that you will lose on the energy efficiency, because sometimes when you do this and you want to have a material for cathode, then the potential will drop during the cycling curve. I mean, if during the redox reaction, you will start at 2, for example, and you end up at 0.5 or 0.9. You will not remain at 2. You will not have a stable potential. The potential will drop because of this polymerization. And the second or other additional ways you can, we are using a liquid electrolyte. You can try to make it a solid electrolyte. And this goes beyond the electrode or the material science at the electrode level. Some of them are working very good, and this is actually the topic of one of the topics of research in the group here in Houston. And other things, you can just try to trap these soluble organic molecules inside porous carbons. We call them impregnation. So you just need to put them inside, and then you will have you will prevent the solubility, and you will increase the electronic conductivity of the electrode. But here you just need to use a large amount of carbon, and then you will use less amount of the electrode material, and then it will reduce what we call the mass loading.
Okay, I think it's a quite complete questions once again, response once again from you. So, and one second question that is related to solubility. So yeah, I guess that no, it should be all right, but I will still ask it. So this is a question from Johan Olivier. He says, if I understood correctly, you say that you want to prevent solubility of the electrolyte. Is it to suppress the diffusion of the electrolytes? And is solubility limiting the ionic conductivity and thus the battery potential?
Yes. So you have two things. You have the electrolytes, is a different component, is a different system, and you have the electron material. So here we are talking about celled battery. So the celled battery, the electrode material should be in the solid phase. There are other batteries that we call redox flow battery, and here you use the electrode material as in the dissolved state. You use liquid, so everything is mixed with the electrolyte. So here you have two medium. You have the electrolyte, which is liquid, and you have the solid electrode, and in between you have the interface. Okay, so you should have an ionic conductivity in the liquid medium, because you want to move the lithium from the negative electrode to the positive electrode. So here we are talking about the ionic conductivity in the electrolyte. And then you should have an ionic conductivity inside the solid, which is different and very hard. It's always to have a better diffusion in liquid, because the ion is solvated, and the migration will be easier and fast, I would say, as compared to the solid. And this is is a crucial parameter if you want to have rate performance, because you want this lithium or magnesium or sodium diffuse fast. And I have shown one example with this, because one molecule you start with in magnesium metal batteries is slightly soluble, and then once you catch one magnesium, it becomes soluble. But once you catch the second magnesium, then you make it insoluble. So it depends. It depends on the battery configuration. It depends on the electrolyte system, and it depends on the electrode material as
well. Okay, thank you. Yeah, it's really versatile. So next, another question from Benoit Champagne. So he asks, how is defined the ability of ions to migrate in the solution? How is it measured exactly? And finally, what is the current state of knowledge on the structure-property relationships?
Structure-property relationships with what? With
I guess for the performance of the electrode.
Yes, okay. I will try to answer to this question. according to my understanding. So for the ionic conductivity, usually we measure that. We measure that thanks to something we call the impedance. So we will try to measure the resistance because we make a cell with that electrolyte, and we, when we do electrochemistry, we study only one parameter. We will try to make all the parameters equal, and we change one parameter. And the parameter that we are looking for here is the ionic conductivity, which is directly linked to the electrolyte. So the electrolyte will be the only parameter that we will study in this experiment. And by doing this, we will measure this, the resistance, and thanks to the resistance value and thanks to some formulae that is dependent on the surface, the thickness, and the amount of the electrolyte. So we will be able to calculate the ionic conductivity, and based on this, we can say that this electrolyte is better than the other because it provides high conductivity, and then we can study this as a function of the temperature. For the structure relationship property, so here, as I said, you have organic molecules. You can use it as a cathode or the anode. And here depends on the redox function. You have some redox function that can intrinsically act or behave at higher potential, those at lower potential. If you want to increase the potential, I have shown you that we can introduce substituent groups. If those substituent groups are electron withdrawing, they will reduce the electronic density of the whole system, and this will cause the potential to increase. If the substituents are electron donating, they will enrich the whole system, and then, or the molecular system, and then they will decrease the potential. So if you want to design something at high potential, you should decrease the electronic density. And if you want to design something at low potential, you should increase the electronic density. And then for the solubility, because here you have a structure relationship between the molecular structure and the electrochemical performance. And this, as I said, you introduce something ionic groups or polymerize. And all of this, you can do it at the molecular level. You have other additional, techniques that you can use to overcome those issues, but those have nothing to do with a molecule, electrode molecule itself, but you just work on other system in the batteries, like using additional carbon, additional additives, additional binders, and a different electrolyte system. And you can have at the end pretty much the same result, which you are looking for, high energy density, but stable. We are looking for this stability during cycling.
Okay, thank you for your question, for your answer. Sorry, and just maybe about the bulky substituents that you could put on your compound.
Yes.
Is there any?
Yeah, I see. This is interesting because, as I said, you have two different redox mechanisms. Sometimes you insert or you use cations for charge compensation, and those cations could be lithium plus, sodium plus, magnesium plus, potassium plus. And if you think the molecular weight of lithium plus is only 6.941, so it's low. Sodium plus is 23. But for the anionic one, the anions that we are using so far, because it's a lithium ion battery, nobody cares about the anion. We care only about the metal. So we use different anions, and the anions will change the solubility and the ionic conductivity. It plays a role in the electrolyte, but for this redox system, the anions that provide so far good ionic conductivity are high molecular weight. We are talking about 250 more per gram. And this, usually we should consider this molecular weight in the calculation of the capacity. Most the papers in the literature, they don't take into consideration the molecular weight of this, and they show capacities which are already low because of the molecular weight of the material itself, of the molecule itself. But if you add the molecular weight of this, it will decrease more the capacity. But for the moment, I don't know. There is no research on this. They always, we just need to understand the redox reversibility and the redox behavior of this organic materials that can store anions. But I don't know. It's a new path to check if we can use other anions with low molecular weight.
Okay, all right, thank you. Yeah. And yeah, another question from Michael de Volder. So he says, amazing talk, Alae Eddine.
Thank you, Michael.
And so the question is, how does the volumetric, so he says the volumetric, not the gravimetric performance of your organic cathodes compare to LFP? I guess it is the lithium iron phosphate battery.
So this, if you look at the literature, what we show in the literature is the potential, capacity, cycling, stability. Those are the three parameters that we usually read in the literature. Now we start having some additional information about what the electronic and the ionic conductivity, which are important parameters to take into account, because this will give direct access to the cycling rates capability and the volumetric density of the material itself. Usually we don't use this. And to measure this, you need the crystal structure. And most of the reported organic molecules, they don't provide the crystal structure. We just study the electrochemical performance, but we don't go deep inside the crystal structure and see how they are organized in, at the crystal. And by doing this, you can calculate the density. Usually what we do now, what we start doing is that we make a pellet and we try to measure the density. And this is intrinsic to the organic material. It doesn't matter if it is organic material for batteries or something else. Organic itself is soft, is not dense, and the volumetric density is very low as compared to inorganic. You have rocks, it's very dense, and this actually will have a drastic effect on the size of the battery. So the size of the battery will be larger, but the weight will be lower. And this always I say this with my discussion with the other postdocs and students. Here, the applications that we are looking for are for applications for electric vehicle, phones. So here it's on Earth. So on Earth, the volume is more important because you have the size of the Earth, but the weight, we don't care. If it is heavy, it's okay. The Earth can support. But for spatial application, if you want to send something to the space, so here the weight is more important because in space you have a large volume, can put everything you need, but if you want to send 1 kilogram of something, it will cost much more high as compared to sending 1 gram. So the cost is more important. So here what I'm showing is just organic materials from a fundamental science point of view, but we don't know. In 100 years people are looking to go to Mars. So we will see, but this would be a useful knowledge to be explored in the future. This is my personal point of view.
Yeah, which I share. I should. So yeah, really depends on the application that you are looking for. So just to go a bit further into the structure property relationships. So Benoît Champagne was just saying that the way to he says that structure property relationships concerns more the way to optimize or maximize the migration ability as a function of the nature of the ions, more than the potentials at the different electrodes. So what about the structure property relationships concerning the migration ability?
Yes, but for this, I don't know. I think that he's talking because, as I said, you have the migration. You have the migration in the electrolyte, and then you have the migration in the solid, which is the electrode material. And we don't have enough knowledge on crystal structure of organic materials. So if we don't have this knowledge, we cannot have access to the information of how those ions, which are cations or anions, migrates inside the solid. Usually in inorganic materials, you have a vacancy sites which are empty. Once you take, for example, one lithium, this lithium will move here and push the other one, and then push the other one. And this is how it works. There is a mechanism for this ion diffusivity inside the solid. So for the liquid, as I said, you have, lithium salt, you have lithium perchlorate, for example. What you will find in the liquid is the lithium surrounded, which we call the solvatation, with solvent molecules. So the lithium is alone and the anion is alone. And this actually will make the migration of the lithium or the cation, sodium or whatever cation you're using very easy and very soft and very simple as compared. In the solid, you don't have this solvatation effect because you don't have solvent molecules, but all of this is surrounded with the with some more atoms inside the crystal structure. But this is a deep, we need a deep knowledge inside the crystal structure and some, you know, a little bit, I would say, complex characterization. And this is the limit actually for the organic materials. So we just design new organic molecules. We see high potential, low potential capacity, but we don't really look inside the material, how this redox reaction is working, how the lithium is coming in and out, you know, and this it takes time and it takes new knowledge and new effort to be bring to this field.
So yeah, thank you, Alae Eddine, for this very nice presentation.
Thank you
So
very
there
much.
are no more questions from the audience, I think.
Hope that it was clear.
Yeah, I think it was very clear. So just I have one personal question that comes. It's really a very general question. Simply, what could be or what are the limitations that could prevent the development of organic electrodes for large scale use in batteries? What would be
Yes.
the limitations compared to the lithium
Yes,
ion?
true. Yeah, so here to answer to this question, I would say depending on the application, because you have the stationary, mobile, and you have the grid. Because if you want to use them in electric vehicles, phones, or choose, I mean, electronic devices, the volume is important. And you know, volumetric energy density in organic materials is very, very low. So it's very hard to see organic materials in electric vehicle, cell phones, because the volume will be late, but the size of the band. Now we have iPhones this size. If you want to make the same energy density with organic materials, the iPhone will be in the tablet size, and you can see the effect. In contrast, if you want to use for the grid, I mean, you produce energy from wind, from other renewable resources, but you want to store them in a large scale for domestic. So here we don't care about the volume. We do care, but not that much because we have space. But here we care most about the cost and the energy density. And if we can find or afford barriers with low cost for this, so organic, they can play a good role here, I think.
All right, thank you for this good resume. So,
Thank you.
no, I just have to wish you a good lunch at Houston, and
Yes.
here is the dinner in Belgium.
Okay.
So, hope to see you soon,
Okay.
and once again, thank you for this nice talk.
Okay. Thank you very much. I hope it was clear and people have learned something about organic materials. And see you next time.
See you next time. Bye to the audience. Ciao.